Hey guys, Math 6610. You may notice that under the first week, and you know, I'm putting this, I'm creating this video in fall of 2017, but hopefully it's a good enough video that I can use for future classes. But anyway, under week number 1, whatever the date of the Monday may be, you'll see a PowerPoint, statistical testing for research. And you know, this video is kind of all about this PowerPoint. So if you want to play along, you can open up the PowerPoint. It's not necessary because I'm going to go through the PowerPoint in the video. So let me go ahead and get this going. And let's start from the beginning. So using statistical models to test research questions, what we're going to go through here, we're going to go through everything from type 1, type 2 errors to power to effect size, just starting a good foundation for quantitative research. Now, the ultimate goal in this class is to get you ready for the research sequence, Math 6996, 6997, 698, where you carry out quantitative methods in research. So we tried teaching the research sequence without having the quantitative methods classes at first. It was a complete and utter nightmare. So we added these two to our courses. So anyway, let's get to it. In conducting a 5-stage process, now guys, I'm going to fight this as much as I can not to read to you, because I hate for someone to give me a PowerPoint and then just read to me. So, but some of it, you know, it's just going to lend itself to reading. But I'll do my best to keep that from happening. Now, what I've done here in the 5-stage process, on the left, I've given you a 5-step for conducting quantitative research. And on the right, 1 through 5, I've given you an example. So the first thing, we generate a research question. And typically, I think a research question combines two things. It combines what does the current research say with you being aware of your surroundings. So you kind of have an idea what the current research is all about, but then you're noticing some things potentially with a different population, potentially with a new twist. You're noticing things in your surroundings that you would like to evaluate that's very relevant and connected to the current research. So the example that our online statistics classes as effective is face-to-face statistics classes. This generated out of some interest for our administration, wanting to create more online programs to try to build our enrollment. So they first came to me, I think, about 10 years ago, wanting me to create some online statistics classes, and I refused because I didn't think they would be as effective. I'm finding out now as I'm teaching the online courses, I think they are equally effective, and if not, they may even be more effective. Number 2, generate a theory to explain your initial observation. We call this kind of your theoretical construct, or your the theoretical basis. You've got to have a theoretical framework by which your theory is explained. So what I've done here, I said students receive information via technology, all the time through social media, and back in the old days we'd go to a library and thumb through those index cards. Today we just get online. So the fact that education could be presented through the use of technology is not shocking to any of us. Number 3, break your theory into a set of testable predictions. So an example of a testable prediction is that the mean score on a common set of final exam questions will be the same for online and face-to-face students. Now, we can go in and we can make these these research questions much more complicated. We may think that there are other variables that are relevant. Maybe their background, maybe were they placed into developmental or not, maybe gender, maybe socioeconomic status. So we can make these testable predictions include multiple variables, but I kept it simple here because we're just learning. Number 4, collect data. So what I do is I give a common set of exam questions to the face-to-face students and to the online, and I sit there and count how many they got correct and start tabulating the exam scores. Finally, analyze the data by using a statistical model. What I would here probably would be using an independent t-test. I may want to come in and control for some quantitative pre-measure, maybe an ACT score, in which case I would use an ANCOVA design. But that's stuff that we're going to learn in the class. What is the difference between, well, first of all, what is ANOVA? What is ANCOVA? What's the difference between ANOVA and ANCOVA? So let's think it through. Does your little brother have an unfair coin? First, it says we will learn to use sample data to estimate what's happening in a larger population to which we don't always have access. Second bullet on the left, our class deals with inference. Inference is just statistical techniques that we use to make generalizations or statements from sample data to larger populations. The third bullet, we can never completely be sure whether our statement, our decision on the null or alternative hypothesis is correct, so we calculate these things called probabilities or p-values, and we'll find out later as probability decreases we gain more confidence in the alternative hypothesis and lose confidence in the null hypothesis. So on the right, an example I think is kind of interesting is, let's say your little brother seems far too eager to want to challenge you to flip a coin for money, and he makes it clear that he will only play this game if he gets to use his coin. So you're kind of thinking, well, okay, what's he up to? So while he's asleep, you borrow his coin and you want to test it. So ideally, what would you do? Well, you would sit there forever, infinitely number of times, and flip the coin and see if it turns out to be 0.5 for head and 0.5 for tail. So would the probability of head and tails be equal? But you couldn't do that because you would flip it forever, and you would, for obvious reasons, it wouldn't. The outcome wouldn't be of much good to you. So what you would do is probably create some sample data, sit and flip a coin, record each head, record each tail, and you would kind of generalize from your coin flipping what may happen if you were going to flip the coin infinite number of times. So you would use your sample data. The null here is the coin is fair. So the null is always kind of the status quo. It's kind of the lazy statement. And the alternative is really the motivation for the test. It's the aggressive statement. You must have some concern of the coin, or you wouldn't be testing it. So we embed that in the alternative hypothesis with the coin is not fair. Third bullet, you decide to flip it 100 times. Maybe you've got more time and flip it 200, even better. Maybe you've got a lot of time, you want to flip it 1,000 times. Flip it as many times as you want, but you have to get it large enough to meet certain conditions in statistical testing. So you get 62 heads. Is that decent? Well, because of sampling variability, if you flipped it another 100 times, that you would probably get something different than 62, maybe 52, maybe 58, maybe 68, who knows? But the samples will vary each time you flip this 100 times. But in statistical inference, we typically don't take multiple samples. We take one sample, and in this case, we've got 62 heads out of 100 flips. Well, is that too many? Is that too much different from 0.5, which we know we would get with a fair coin, is 0.62 or heads, is that just by chance, by random chance, that we got 62 out of 100? Or is that actually based on the probability? Is that statistically significant? Does that mean something to us? Is that a rare outcome based on the assumption that we're flipping a fair coin? Essentially, in statistics, we get down to the question: is the probability less than 0.05? So, what's the probability? Based on the truth of the null hypothesis, assuming the null hypothesis is true, the coin is fair. Is the probability of getting 62 heads out of 100 flips or more, is that probability less than 0.05? Well, 0.05 is usually our threshold. So if it's less than 0.05, we would reject the statement the coin is fair, and we would conclude there's more support that the coin is not fair. If the probability is higher than 0.05, we still may not believe the null, but we don't have statistical support. We don't have statistical evidence to reject the statement. So why do we use 0.05? The industry standard for statistical significance is 0.05. And I say they're the industry standard for confidence, and confidence intervals is 95%. Well, if you change the 95% to 0.95, you'll see these two add up to 1. Is there any reason for that? Yes, there actually is, and we'll talk about that later in the class. But it's been kind of a mystery to a lot of people. Why is the industry standard 0.05? And a lot of people say that it goes back to banking, and many moons ago, financial institutions were able to withstand a 5% error of lending money. Now let's talk about lending money. What happens in financial errors? If we look at the top, in terms of lending money, a customer comes in the bank, and we're the bank director, the financial officer, the lending officer. Are we going to lend them the money? Well, we either are or we aren't. And if you look on the left-hand side, the customer will either pay back the loan or they won't pay back the loan. Well, looking at the broader possibilities and outcomes, so all the possible outcomes, if we look at this first square, if we lend the person the money and they don't pay back the loan, then that's a financial error. We made a bad decision in giving that person the money. However, the other decision, we didn't lend the person the money, they wouldn't have paid back the loan, so it was a good decision not to lend them the money. On the bottom line there, using the column, did we lend them the money? Yes. And would they pay back the loan? Yes. And that's a good decision. We want to lend people money. Well, not we, I'm not a banker, but they want to lend people money who are going to pay back the loan because they get the interest. The bottom right square is an error because we didn't lend the person the money, but they would have paid it back. So that's a missed opportunity to gain interest on a loan. Now, we can move these in more generally to statistical errors. Let's think about the null hypothesis. It is either true or false. That's not technically correct, but it's a good way to think about statistical errors. Ultimately, at the end of the test, we're either going to reject the null or fail to reject the null. If we have a true null, then we want to fail to reject it. True statements we want to keep around. So if you look in the bottom left-hand, well, the middle column, the left-hand where I have correct decision, if the null hypothesis is true and we fail to reject the null, then we've made a good decision, a good statistical sound decision. If the null hypothesis is false and we reject the null, you can see that those two rows and columns lead to a correct decision also. Because false statements, we want to get off the record. We want to reject those. So that's a correct statistical decision. But if you look at the other two, look at the two errors. The one error that I want you to focus on is the type 1. And that occurs when the null hypothesis is true and we reject it. Guys, we don't want to reject true statements. We want to keep true statements around. And the other error, the type 2 error, if the null hypothesis is false and we fail to reject it, we don't reject it, we've also committed an error, and we call that a type 2 error. So more on statistical errors. What is a type 1 error? It is rejecting a true null hypothesis. A type 2 error is rejecting a false null hypothesis. Guys, this should go in your notes. There's two things that should happen in this class in terms of your notebook. You should have notes from the videos, and you should have notes for R. We're going to start using R really soon. So it's just, you know, when you start doing your assignments and start studying for your midterm and your final, it's problematic to have to go back through all these videos. It's much easier to just pick up your notebook and study from that. We're going to run into something called alpha. Alpha is a level of significance of our test. Level is also the probability of committing a type 1 error. Beta, we talk about beta a lot in statistics. It is the probability of committing a type 2 error. And again, a type 2 error is just failing to reject a false null. Power, the probability of rejecting a false null. Typically, the motivation for conducting a test is to find evidence against the null hypothesis. So the probability of rejecting a false null is just 1 minus beta. So take the probability of committing a type 2, subtract from 1, you get the power of your test. Now, I'm going to put up another illustration here in the next video that gives you a nice graphical demonstration of type 1s and type 2s and betas and things like that. Now, one common mistake is people look at this and then they're, you know, alpha is given. Alpha is usually 0.05, but people want to know, how do you calculate beta? It turns out beta is a little tougher to calculate. And sometimes people want to think that beta is like 1 minus alpha. Well, that's just goofy. That's not true. So, a little bit more about alpha. The probability of committing a type 1 error. Common choices for alpha are 0.001, 0.01, and 0.05. Sometimes you even see 0.10. Not often, though. And the value for beta, which again is the probability of committing a type 2, depends on the choice of alpha. Now, alpha versus beta. I had a student ask me one time, and I thought it was an excellent question, if alpha is the probability of committing a type 1 error, and we all know that 0.001 is a lot lower than 0.10 and 0.05, why would we not use 0.001 or even 0.0000001 as alpha? Because if errors are bad, why do we open the door to commit them by setting alpha, our level of significance, to 0.05? Well, the illustration I've given you here shows you what happens with type 1 and type 2 errors. What happens is as alpha goes up, beta goes down. As alpha goes down, beta goes up. So you can set alpha really low, for example, at 0.001, so you would very rarely, only 1 out of every 1,000 trials of the test, would you commit a type 1 error. However, that opens the door for committing more type 2 errors. If you set alpha on the other end of the spectrum at 0.10, then the probability of committing a type 1 is 1/10, 0.10. But you would very rarely commit a type 2 error. So I think the reason people set at 0.05, I think it just balances the probability of a type 1 and a type 2 error. So, you know, do we always choose 0.05? It turns out by the time you finish this class, you'll find that it really doesn't even matter. You may adjust the alpha level based on the consequences of a type 1 and a type 2, as I've given in those sub-bullets. But ultimately, we calculate our p-value and we just report it at the the highest level of statistical significance. And I cover that later in this video. Okay? So guys, the maximum accepted probability of a type 2 is 0.20 or 20%. Therefore, because power is 1 minus beta, we get into a desired level of power of 0.8 or 80%. So a power level of 0.8 says if the null hypothesis is false, then the probability of rejecting it is 0.80. And all the big boy, big girls in statistics kind of set that as the standard or the desired level of achieved power. Now, we're going to talk a lot about statistical significance. So once we get into research and we get to be big boy, big girl researchers, you're never going to open up research or read any research and see the words reject and fail to reject. It's either significant or it's not significant. So statistical significance is when our p-value, the probability of attaining our sample data if the null hypothesis is true, is less than our alpha value. So if we set our level of significance at 0.05, our alpha value at 0.05, a p-value of 0.032 would be significant at the 0.05 and 0.10 levels, because 0.032 is less than both of those, but it would not be statistically significant at 0.01 and 0.001, because clearly our p-value is higher than that. Now, a lot of people say, well, let's just go get the p-value and then we'll just adjust the statistical, adjust our alpha level according to the outcome that we want. Well, the problem with all that is when you create research, you write Chapter 2 and Chapter 3, which are your methodology and your lit review. Now, you write that before you actually conduct your analysis. So, guys, it is not acceptable to set your alpha after calculating your p-value, although it is kind of funny. So how do we calculate a p-value? What is a p-value? Again, a p-value is, if the null hypothesis is true, it's kind of the probability of collecting our sample data, or something more extreme than our sample data. So, guys, it all goes back to variation. We have what's called systematic variation that can be explained by our model. And then we get into error, and that's what we call unsystematic variation. It turns out that a test statistic is just the ratio of the explained variation to the unexplained variation. Guys, there are many test statistics. The four that we're going to look at in this class are Z, T, F, and chi-square. So how do we report a p-value? Reporting p-values at their lowest level of significance using 0.001, 0.01, and 0.05 as the cutoffs. So, and I'm going to give you examples of this on the next page. If a p-value is higher than 0.05, report it. If a p-value is less than 0.05 but higher than 0.01, report it as p less than 0.05. Same thing if a p-value is less than 0.01 but higher than 0.001, reported as p less than 0.01. If your p-value is less than 0.001, easy for you to say, report as p less than 0.001. All right, so examples. First of all, p-values should be reported either to 2, 3, or 4 places. It's up to you. Just be consistent throughout your document. And never report a p-value with a leading 0. The reason that's incorrect is that ones digit could never be anything other than 0. So as long as there's no variation or no potential for variation, we don't put a value there. So p-values are just reported as point, and again, you can go 2, 3, or 4 places. Just being consistent. So, guys, the first example, p-value 0.321, just report it. It's higher than 0.05. The second example, the p-value 0.032, we would report that at p less than 0.05 because it is significant at 0.05. It's not significant at 0.01 because 0.032 is not less than 0.01. Same thing for a p-value of 0.005, reported as less than 0.01. And a p-value of 0.0009 we would report as significance less than 0.001. All right, gang, test statistic. Again, it's the ratio of the explained variation divided by the unexplained variation, or the effect divided by the error in our model. So unexplained variation is error. Now, what do I mean by that? What if we'd like to predict, we'd like to examine why some students are successful in a statistics class and some people aren't. And we come up with this model that we want to test. Well, we're going to find out that our model explains, okay, first of all, our dependent variable here would be success. And it could be a final exam score, it could be GPA, it could be success rates, yes or no. Our dependent variable can be dichotomous. So did they get a C minus or higher? Well, they either did or they didn't. So our model, our dependent variable has variation. The results vary. If it doesn't have variation, we don't have a variable, so we can't include it in statistics. Pretty soon you'll find out statistics is all about variation, explaining variation. So our model is going to explain part of the variation in whatever we're trying to predict, whatever we're trying to explain, but then our model is going to miss some of that variation. Well, that's the unexplained variation. That's called the error. So a little bit about test statistics. Larger test statistics result in lower p-values. So a larger test statistic, for example, t equal 2.8 will have a smaller p-value than t equal 1.28. And same thing for an F statistic of 5.8 versus 2.0. I'm going to show you on R how to calculate p-values in the next video. But right now, what I want you to know, test statistics represent the underlying probability distribution that's used to calculate the p-value. Now, how are you supposed to know what probability distribution represents that underlying probability distribution? Just put it to memory. For example, we're going to learn something called ANOVA. ANOVA uses the F distribution, named after Fisher. We can get into pooled and unpooled t-test. They use a t distribution, and ultimately we will get into to things that use a chi-square distribution. We have a chi-square goodness of fit, a chi-square test of independence. The underlying probability distribution there that we use our test statistic to calculate the p-value from would be the chi-square distribution. We also, for the Z and T, we get into one and two tail test. I'll demonstrate more about that in the next video. F and chi-square are simply one tail test. So guys, I'm going to come back and do these illustrations, these following illustrations using R and your graphing calculator. So I'm going to take those 5 and I'm going to calculate the p-values for you in the next video. So write these down, pause the video. So Z equal 1.45, one tail and greater than. I'll go through the illustrations and show you how we calculate that. So statistical significance versus practical significance. This is huge stuff. Let's say example number 1. Let's say that we have reason to believe that our existing claim about the average ACT at Shawnee State University, which people claim is 20.6. Let's say we have reason to believe that it's raised, that we're recruiting better students or whatever it may be. There's clearly an obvious theoretical framework here. People seem to be putting more emphasis on ACTs. Lots of motivations for a study like that. Lots of reason to care. So let's say example number 1, we get a test statistic of 1.85 from a sample size of 1,500. Example number 2, testing the same set of hypotheses, we have a test statistic of 1.85, but a sample size only from 8 students. Okay, so let's see what happens here. Example number 1, if you crunch the numbers on that, you could see that come down to the 4th bullet from the first big bullet. You can see that T, degrees of freedom 1499, we'll get into that in the next video, is 1.85, and if you calculate the p-value, it's less than 0.05. So we have statistical significance. But if you try to tap into the location of the mean, the 95% confidence interval doesn't give much variation from 20.6. In fact, 21.2 is the upper end of the 95% confidence interval, although statistically significant above 20.6. 21.2, which is only about a half of score higher than 20.6, really doesn't lead to a lot of practical significance. Another example, if you bumped up your sample size high enough, you might show that the new mean is like 20.62, which is higher than 20.6, leading to statistical significance. But do we really care 20.6 versus 20.62? Well, practically, I don't think that has much significance. So in this illustration, one may argue, you really don't argue, you either have statistical significance or not, but you may argue that we have statistical significance, but not practical significance. In other words, the difference is statistically significant, but not enough difference to really mean a difference in practical significance. Imagine that you were doing a weight loss study, and you took you claimed that this weight loss is the greatest thing since sliced bread. So your null hypothesis may be H sub O equal mu equals 0. There's no effect. And then H sub A may be mu greater than 0, which if you're measuring loss, and let's keep everything positive. So someone, weighs 200 pounds and they lose 5 pounds, then we'll just put their weight loss as a 5. So then mu would be greater than 0. And let's say we get a big enough sample size where we reject the null, but the mean weight loss only turns out to be like 0.1 pounds. Well, we got statistical significance, but does anybody really care if we lose 0.1 pounds? I guess it's better than gaining. I guess it's better than nothing, but to me, there's no practical significance. I don't think anyone's really going to care if we come out with this, this heck of a weight loss program where we tell you, well, you're going to lose 0.1 pounds on this diet. I don't think you're going to be very successful marketing that. But most people, if they're going to market that and be safe, they will say that, well, research showed a statistically significant weight loss. Then we'll get into the details. So the proof would be in the pudding there, and a lot of times that's left out. So guys, because of the dynamics, the dilemma between practical significance and statistical significance, we get into something called effect sizes. So the motivation for effect sizes, just because a test statistic is significant, doesn't mean the effect is meaningful or important. And again, a good way to think about this is to think about the weight loss example. We may get statistical significance, but really is 0.1 pound weight loss meaningful or important? No, it's not. So the solution, we measure what's called the effect size, which gives us a standardized measure for affecting or measuring the effect of the experiment, or the strength of the relationship between two variables. Guys, we're going to encounter a lot of different effect sizes. In fact, I will add to Blackboard very soon an article that just goes over tons and tons and tons of different types of effect sizes. We'll see throughout this class that the type of effect size that we use and report depends on the type of statistical technique that we're conducting. But nevertheless, the two most common effect sizes that we run into are Cohen's d and Pearson's correlation coefficient. Now, to give you an example, I've given you the thresholds or the cutoffs for a small effect, medium effect, and a large effect using R. Now, total variation is explained by r squared. So, for example, let's focus on r equal 0.3. That represents a medium effect when we use Pearson's correlation coefficient as our effect size. If we take 0.3 and square it to create r squared, well, that gives us 9%, so we can say 9% of the total variation is explained by the effect. So, the explanation of the total variation is explained by r squared, where r is used to calculate the level of effect. So if you do a study and your effect size turns out to be like r equal 0.6, then you would report that as having an extremely large effect. Where on the other hand, if you have an r of like 0.05, then you would say that you have none to a small effect. Okay. Effect sizes can be easy to calculate. They can be hard to calculate. It turns out for a t-test where we have a test statistic, our t-statistic, it turns out that calculating the Pearson correlation coefficient is very easy. It's just the square root of t squared divided by the quantity t squared plus the degrees of freedom. So back to example 1 and example 2. Very interesting here. With our sample size of 1,500 in example 1, where we have a degrees of freedom of 1499, we get a very, very small effect size of 0.04. However, the same example where we had a small sample size of 8, but we did not get statistical significance, you can see that we have a large effect of 0.573. So what do? Well, you report stuff. And I like to, when I kind of try to mold quantitative researchers, I like to turn them into just unemotional geeks, just neutral. You report stuff. You set up your study. You think about how your study is going to be designed. You think about the variables you're going to collect. You think about the statistical procedures and techniques that you're going to use. You think about the assumptions and the conditions and the violations of those conditions. So you set things up according to the conditions of the statistical tests that you're going to use, tests and techniques, and then you carry it out. You put your information in R, you enter the code, and then you report the information. Be neutrally involved, right? Be very unemotional. A lot of people think that when you conduct research that you must end up with statistical significance. In fact, I have a PhD student I'm currently working with out of Florida, and she had a survey that she had created, and this survey was shown to be reliable and valid, and the internal reliability was really impressive. So she gave this survey to a group of students, 51 students, and she did a pre-post. And her results did not turn out to be significant. In fact, her results didn't turn out to be impressive at all. Well, she's losing her mind because she thinks that she's got to have something that's, whopping big news for it to be to be credible. But it doesn't have to be that. With quantitative research, with any kind of research, you're just trying to add to the current knowledge on your subject matter. So even though she didn't get what she wanted out of her study, there's a story to be told from her analysis. And I'm trying to get her. I was at soccer last night, soccer the night before last, and she called, and I missed almost the entire second half of my daughter's soccer matches because I was trying to calm her down and say, okay, everything's going to be fine. It's just the way it happens. So we kind of want statistical significance because it's impressive, and it kind of validates our reason for wanting to study, the motivation for the study that we chose to conduct. But that's not the way research works. Sometimes you do a lot of work and you find out in the end that you don't have statistical significance, you don't have practical significance, you got no effect. when you report it, and that becomes part of the overall knowledge of your subject matter. So statistical power, guys, statistical power, again, power is let me get back to I want to keep things structured here. Effect sizes express the importance of a research finding and is linked to 3 statistical properties. So given any 2, we can calculate the third. First thing that impacts statistical power is the sample size. The second thing is the level of significance. The third thing is the potential to detect an effect. So guys, if we know 1 and 2, the sample size and the level of significance, we can calculate the power. If we know the power and the level of significance, we can calculate the sample that created from the study. If we know 1 and 3, then we can determine the level of significance that was used. So again, the power of a test, I'm going to be repetitive here when things are super duper duper important. You repeat, right? The power of a test is the probability that a given test will detect an effect, assuming an effect exists. It's also the probability of rejecting a false null hypothesis. So guys, our aim, our goal, our focus, we want an achieved power of 80%. If we get too much power, then we start getting into situations where we get statistical significance but not practical significance. If we get power much lower than 0.80, then we might have a false null, but we don't have enough power to reject the false null. So the probability is going to be underestimating our test statistic in terms of rejecting a false null. So again, power not high enough leads us into situations where the null could be false, but again, we don't have enough power to reject it. So more on statistical power. We have 2 types of power. We have achieved power. So achieved power, if we go back, achieved power is we have our sample size and our level of significance, and we can calculate number 3. Priori power is after we conduct the test. We can calculate the sample size, before we calculate, goodness gracious guys, it's easy for you to say. Before conducting the test, we can calculate the sample size required to achieve a particular power. So in that situation, number 1 is unknown, but we know number 2, usually 0.05. We know number 3, the statistical power that we want to achieve is 0.80. We can go in and choose or calculate the sample size that will yield a power of 0.80. So the first bullet, achieved power, is after we've conducted the experiment. We can actually, given the sample size and the level of significance, we can see if we had enough power to detect a difference if it, or an effect if it actually existed. Priori power is before we conduct the test. And most research will require priori power before you start collecting your data, because you want to make sure you get enough subjects to get an achieved power of 80%. So guys, we'll use G-Power. I'll demonstrate that in future videos, but now let's examine a few textbook examples, okay? So that's going to be in the next video. So, learning check. Why do we use samples? Number 2, what is the test statistic and what does it tell us? Number 3, what are type 1 and type 2 errors? Number 4, what is an effect size? Number 5, what is statistical power? All right, guys, this is going to be part of your first assignment. So send an email to ddarbro@shawnee.edu. You know my email account. Send it by the Friday of the second week by 5 p.m. and tell me the answers to these 5 questions. This will serve as your first question of assignment number 1. So this is actually embedded in assignment number 1, which you'll get about the 5th or 6th week, depending on the pace that we set, or I guess the pace I set. All right, so guys, get the answers to those 5 to me by the Friday of the second week. And I want to be kind of vague here in general because I want to be able to use this video from semester to semester. All right, guys, have a great day. The next video we'll get into using R to calculate p-values and some cool stuff. So take care.